2017 level 3 physics electricity, guys. Good lock in. Alright, let's get started. Thomas is a car. Oh yeah. This is a cool concept. Alright. Describe what is meant by the term time. Oh. Okay, this one I don't really know. I don't really know either. You honest here? Term time constant. I would assume. Okay, well we're gonna capacitor circuit, so we're gonna use this equation. T equals RC. So the term time constant. Oh yeah, okay, so the term time constant is the amount of time it takes for the capacitor to charge 63%. Is the amount for the capacitor in the circuit to charge up to 60% of max charge. So we're at 1 time constant. Alright. Boom! That's one cheap trick right there. Boom shakalaka. Okay. Hey, question I. Okay, diagram shows RC circuit. Capacitor is initially on charge. After a switch is closed, battery supplies that many joules of energy. Okay. Calculate energy stored in capacitor when it's fully charged. Okay. So I'm gonna whip up the formula sheet. Oh, that's. Wait, I'm just gonna do this real quick. Alright. Go on the formula sheet. Can you see my mouse on there? Oh yeah, okay. Energy stored in the capacitor. What the heck? Okay, we got this one. E equals half QV. Just gonna plug this shit over here. Oh, pressure square. Equals half QV. We're given voltage supply, and I think they're just letting us assume. Oh yeah, because fully charged. Okay, so it's gonna be using up all the voltage. Because when it's fully charged, it's at max capacity. No, not max capacity. What's the word? It's like it'll just be using up all the current. It won't allow anything. You just gotta follow along. You know, you gotta be in the know to know. I'm just gonna. Oh, okay. I'm gonna try and increase my hand right. Times 2 because we got the half, and then to give us a voltage, which is 12 volts. We get Q. Wait, calculate the energy stored in capacitor fully charged. Okay. Oh yeah, okay. So we find Q. Oh, I'm not gonna use my calculator here. I have to use this stupid ass one. 7.2. Where is it? 00144 divided by 12. Oh, okay. I swear that's wrong. Oh, no, that's right. So, oh, and it doesn't convert it into. Does my calc do that? Hold on, let me see if it can. I don't think it will. Alright, we're just gonna have to write in old zeros. Okay, 0.0012 farads. Alright. Boom, didn't take any time at all. Now we can just find the energy when it's fully charged. That's not right. After switching to the battery supply. Calculate energy stored in capacitor is fully charged. Okay. I'm just a dumbass. Oh, I'm so stupid. What the hell they give us? Oh. Given this. Given this. All we need. That's all we need. And Q. Oh yeah, okay, wait, should we just do a rearrangement first again? We know Q equals CB. So, plugging that in, we actually just get CD squared because we're going to multiply by the B. Right, and now... plug our units in. Micro is... I think micro is times 10 negative 3? Like negative 9 is nano. Yeah, negative 3 I think. Times 10 negative 3 multiplied by 12 squared. Boom. Energy when it's fully charged. Oh, I'm gonna use a calculator here. Alright, so we got 0.5 multiplied by 5e negative. 0.5 times 5 exponent negative 3 times 12 squared. Boom. 0.36. So we get 0.360 joules. It's 3SF. Boom. Explain why the energy stored in the capacitor is less than the energy supplied by the battery. I don't think it's negative 3, I think it'd be negative 6. Millifarads? Milliamps? It is, bro. What am I? Micro. Five times 5e negative 6 times 12 squared. Okay, so that is smaller. 0.00036 joules. Yep. Oh, and this half. Okay. That's because I don't know how to explain it, but I feel like it's a little bit of the BS way of doing it, but I know it's how I got taught. E equals half QV. That's what the capacitor, so it's just we'll call it cat. And then this is that. That would actually just technically have kinda stretching the limits here. Voltage is equal I mean, you could just use you don't need to use an equation actually, but for energy energy is just technically QV. You don't actually need a total. You don't need this half. So the energy stored in the capacitor will be half of the energy applied to the battery as I don't even know. Maybe we got the resistor in the circuit, so like technically 7. Okay, I don't really know this answer, so I'm just gonna say the energy stored in the capacitor will be half the energy supplied to the battery as the capacitor has heat loss, energy lost to heat, as there will be energy lost as heat slash E equals half QV cat while energy supplied E equals QV. Alright, we'll just call it that, honestly. Oh. Also, this is a kind of a long paper actually, but multiple parts. So current gets time for 15 seconds after switch is closed. Okay. What that would mean. I'm just gonna plug this equation right here. Tau equals RC. That's the one-time constant. We just want to find the time constant actually. That's the first goal. So R was given previously, which was 8 times 10 5. 8 times 10 to the power of 5. We want to multiply that by 5 microfarads, so 5 times 10 negative 6. That will give us a time constant. Oh, and we're trying to find current. And that is in times 10 negative 5. Can't see. 8E5. Oh, I'm using the calculator. What the? Gosh darn it. Okay. 8E5 multiplied by 5E negative 6. Boom, 4. Okay. 4 seconds, that means... Oh, bro, why do they have to give us this graph? Give us 20 seconds, buddy. That means... how much space can you guys see? Can't see actually much, but okay, so that means tau 1 equals 4. Tau 2 equals 8. Tau 3 equals 12. Tau 4 equals 16. Okay, have I done it right? Okay. Cool. You can see that that's like 1 second, that's 2 seconds, that's 3 seconds, that's 4 seconds. Oh, they've done it so stupid. What? Cancel these out. 1, 2, 3, 4. 1, 2, 3, 4. 3. Oh, and then they give us 16 seconds actually. That's kind of a good like identifier, if you know what I mean. They said 15, but they gave the 16 because they know it's 4 seconds. So that means you know that you got your answer correct for that. And we've been given kind of current, but okay, we need to find current when time is 0. Oh, okay. Here, this is good electricity knowledge right here. At the beginning, when the switch is closed in the circuit, all of the voltage would be across the resistor. None will be across the capacitor, because capacitors will always have a curve like this, I think. Circuit. Wait, no, is this circuit current? Ooh. So you gotta read it. Circuit current. Okay, so that means initially the circuit current will all be going through this resistor right here, but it will exponentially decay, like so. Pretty trash, but look. Alright, so we're just gonna find circuit current when time is 0, which is when all of the current, or when technically all of the voltage in the circuit is across the resistor. Alright, sweet as. Let's try and get that. V equals I R. Voltage was 12. Divide that by 8 times 10, 5 equals I. It's gonna be a small number. 12, 8, E5. Okay, so my calc has got this. I'm just gonna do it twice because it's easier on my actual calc. Calc short for calculator, FYI, guys. I know. 12 divided by 8 E5. That's times, bro. I'm a dumbass. 12 divided by 8 E5. Boom. Yeah, they have it in zeros, but yeah, I'm just gonna use what my calc says. It's way easier. That means we know it's gonna start exactly here. That time constant 0 is gonna be there. And then this is where we use a rule. There's like this massive formula you can use, but I hate it. I use a rule where I use the 63% rule. So in the first time constant, the circuit current will decay 63%. Boom. How we find this out? We go. Oh, we could just times it by 37 for the initial. Nah, but I'm gonna keep it simple for myself. 0.5 times 10 negative 5 times 0.63. This is an extra step, but I find it way easier. So I get 9.45 times 10 is negative 6. Oh, this is crucial amps there. Actually, you don't need amps for that one. And then we go 1.5 times 10. 5 minus this answer. And we get 5? Oh yeah, okay, we get 5.55 times 10 negative 6 amps. Alright, pretty much a step here was, we know 63% circuit current will decay in the first time constant. What I did here, we have the initial, what is it called? Yeah, like technically when circuit current is equal to 0. I mean when when the switch is initially closed. I'm yapping right now. When the switch is initially closed, circuit current will be at max. Times it by 0.63. And that is going to be the difference, which is 9.45 times 10 negative 6. So we subtract from our original circuit current the difference, and that gives us our circuit current after one time constant. So 5.5 negative 6, that's the same as saying like about 0.5. It's not like here. Oh, where's my map? Shit. Right there. Okay, and then we kind of just repeat this process. You can see this. Okay, that's cool. Let's go do it right here. Got. Oh yeah. This is where it gets kind of confusing. I haven't done this in a while, but this is where we kind of a table would be helpful, but I'm just not gonna do it because I'm gonna bug it out. I'm gonna then do 5.5 times 10 negative 6 times that by 0.63, and then we get 3.1 0.497 times 10 negative 6. And then that we subtract it from that. Is that the difference we found? 3.497 times 10 negative 6. Boom. 5 e negative 6. Oh yeah, and this is 5.55. Yeah, look, he didn't realize I wrote it wrong. Okay, so I got 2.05 times 10 negative 6 amps. That means we're looking at 0.2. 0.2 is around here. I don't know if I can really be answering the fourth time constant, but oh well. 0.0535 times 10 negative 6. Times 0.63. Boom. 1.3 times 10 negative 6. 1.3 times 10 negative 6. Subtract. Oh. I'm just gonna do this. 0.535 times 10 negative 6 minus 0.3 times 10 negative 6. Okay, it only says for just 15 seconds, so I am not going to do the fourth time constant. Just gonna rub it out so I don't get affected for my marking. Oh wait, verse 15. No, you do need it. Tripping. I don't want to do it, but oh well. We got 0.1 there, so we'll just chuck it right here. That looks alright. It once more, bro. I hate this. We get 2.8 times 10 negative 7, so that's like... Wait a minute. Yeah, it's literally like nothing. Oh, the red's too loud. Bro, what? She right there. Alright, let me draw this curve. Okay. It's good enough to me. It's good enough to me. Oh, actually, you know what? We got a tool for us. Yes. No, maybe not. Okay, I'm not gonna bother. Find white the graph. Okay, yeah. The graph has an exponential. This is big right here. Decay shape. Okay, I can just tell my handwriting's so bad, bro. I don't care though. The graph has an exponential decay shape as the capacitor. Oh no. As the circuit current will lose 63% of its current. I'm not too sure if it's correct at all. Graph has an exponential decay shape as a circuit current will lose 63% of its current. Of its max current in its first key, then losing 63% of its previous current. Thus, an exponential shape occurs. Time constant of RC circuit can be changed by adding a second capacitor. Ooh, okay. This is where the rule comes in play. Hold on, I'm trying to. Okay, I might just real quickly flip it upside down. Hold on. Yeah. Okay. This is where that capacitor rule is. It's parallel. Big important part. CT equals C1 plus C2. So, adding a second capacitor in parallel will is it the same? Well, I'll just say increase the total circuit capacitance. Okay, so we know that much for sure because we get this equation. Time constant. So we're looking for the time constant. Okay. T equals RC. So if the capacitance of the circuit increases where resistance is constant, then tau must increase. I feel like that's not enough. I think I might have missed out on something as well. Wait, no, wouldn't tau? Yeah. Because I'm just gonna say because there's more. Because there's a larger total capacitance, so it just will take longer. Because there is a larger total capacitance. Okay, I'm hoping I got that one right. God. Oh, what is this type of question? Oh, I think I've done this in the past. Oh yeah, doing this today actually. Yeah, in a car engine, an induction coil is used to produce a very high voltage spark. A voltage spark, that's an important thing right there. An induction coil acts in a similar way to a transformer. Oh yeah. Okay, the diagram below shows circuit arrangement. Okay, so we got 50 turns in primary and 8,000 turns in secondary. Damn, why is it? Okay, state the value of voltage going across the ideal inductor once current reaches a maximum of 5 amps. ha ha. We're not given the resistance, are we? Oh wait, 12 volts. Oh, okay, okay, okay. Okay. No. What the hell am I looking at? State the value of the voltage across ideal and dark. Oh my god, I hate these questions. Question 3 is like my goat question. Go to those ones. I don't like question 2. Given current, given voltage. Guys, I do not know. How long have I spent? 36 minutes! This is not efficient on time. How have I spent 36 minutes on one question? You're putting this aside because from OBS's, bro. Well, it'll be 12 because I don't know. Actually, I kind of just know it's 12 because of that. And if it's ideal, I guess there'll be no voltage loss or anything. So 12 volts must be going across there. I don't know. I think 12 should be fine. Current does not immediately reach max value as soon as the switch is closed. Oh, okay. How would I explain that? The current. Oh yeah, okay, there's a back EMF. Okay, yeah, so the current doesn't reach max initially as there is a large change in current, because initially there was zero current being added to the circuit, and then there's just out of nowhere just current flowing through the inductor. So the current will actually let me use the formula. So we got E. Oh, you can't see over there. Actually, if I just bring it over here, got E is equal to negative L divided by delta I delta T. So this is L is the inductance. A large change in current over a short period of time would generate a large. Okay, this is epsilon, by the way. Generate a large back EMF. So this is a back EMF. And this is pretty much just a rate of current change. So pretty much the current doesn't reach maximum initially as there is a large change in current, thus there will be a large change in magnetic flux. Boom. That's a big one. Large change in magnetic flux, inducing a back EMF. The word back is very important here, as it's going in the opposite direction to current flow. This will initially oppose current flow. Yes, this will initially oppose current flow, preventing current in the circuit from flowing. After some time, yeah, I'm saying after some time, delta I isn't as large, thus back EMF decreases, so current can reach max. Yeah, I definitely was. I could probably state that way nicer, but oh well. This is T. We got T equals LR. What? Never mind. Okay. Hold on a minute. Using the dotted line on the graph. Oh, so it's this one. Oh, we can do the rate of change. We can do current over time. So we can see. We'll do a rate of change of 6. It'll go from 6 to. It'll go from 0 to 6. Sorry, in 0.1 seconds. So we got 0.1 divided by 0.1. That's just 60. I'm just gonna. Okay, yeah. 12. I'm kind of confused about this question actually. Because it's saying right as the switch is closed. Okay, using a dotted line, calculate the self-inductance. Inductance is L. Oh, okay. Back EMF will be 0. Negative L. No, but then that would just make everything equal 0. Oh my god. Hey, let's go looking. Gotta lock in. I actually don't even know if I'm gonna edit this video because I can't really be asked to edit a video. Oh, God, I don't want to edit this video as well. Okay. Immediately after the switch is closed, the back EMF across the ideal inductor is 12 volts. Okay, it's asked me to use the dotted line, calculate self-inductance. How am I meant to calculate inductance? Inductance is L, and I don't know how to calculate L. We don't really know time constant. I mean, I guess the only equation we've really got is this. Epsilon equals negative L, change in I over change in T. We know these, the change in I, change in T. Actually, the change in current over change in time is constant. It's constant gradient. So we can actually do negative L. We got 6 divided by 0.1. Okay, so 6 divided by 0.1, 60, like I said before. 12 divided by 16, 0.2. So negative L equals 0.2. Actually, we don't need the negatives. That's just back EMF. That's because the back EMF is negative. So that's negative 0.2 Henry. Okay, sparks where a high voltage should be produced. Explain how it's possible for a spark to be produced across the gap when the switch is opened. Okay. So when the switch is opened, we're learning this today. We're literally learning this shit today. I remember it. Oh yeah. Okay, so when the switch is opened, there's such a large change in current in a short period of time. So when the switch is opened, there is a massive is a good word to use this, change in current in a very small amount of time as inductance is constant. This will produce a massive back EMF. Okay, so if we go back to circuit, we can see this is a closed loop. So when switch is opened, literally there'll just be a spark that goes from there to there. Maybe we go blue. Like that. When the switch is open, there is a massive change in current in a very small amount of time. As inductance is constant, this will produce a massive back EMF. I'm just gonna state the equation once more. I don't feel like I need to, but I'm gonna do it. L times change in I over change in T. Okay. The gap has a large amount of resistance, but it's the only path for the current. Thus, across the gap, there will... Let's cross the gap, there will be a massive... Also, don't worry about it being yellow. Don't worry about that. Wait, yeah. Across thus across the gap there will be a spark produced. This is because it's a large enough voltage across the switch. Okay, sweet, that's question 3. This is a GOAT question. I love LCR circuits and AC. Well, I don't love them, but they're good. What? Okay, what the hell? Oh, dielectric. Okay, well, I feel like a lot of this is just BS. We're just gonna do RMS times square root 2. That's probably gonna be like 15.6, I think. Let's check. Oh, 16.9. 0.97 volts. Okay, boom. We'll make it equal 17.0. Calculate the RMS circuit in the current in the circuit. Not a trick question, is it? Okay. So we know peak voltage. Okay. So current is always in phase with resistor. Wait. Current across a circuit is always in phase with the voltage across a resistor. Or just a resistance, so we can pretty much go. Take the 17 from before, the last question. V equals IR, so we have 17 divided by 50. That equals I max. That's an important thing to realize. Divided by 50. I'm using the value out of my calculator, so I get 0.339 amps. And then using I max equals I RMS square root 2. Gotta do 0.339 divided by square root 2. IRMS equals 0.24 amps. I'm gonna do 0 just because it's 3 seconds. Alright. Then what would happen to the circuit current when the wood in the capacitor is replaced by a similar piece of wood that contains more water? So if we read up here, water is a high dielectric constant. Higher dielectric constant. So if there was a piece of wood that contains more water, then this is linking back to this. Oh, you can't see it. This is linking to the equation here, where or like epsilon R is the dielectric constant of the wood. So if that increases, that means capacitance increases. Then the capacitance increases. This is actually a good question, because I don't know what would happen. impedance would increase. I don't think circuit current would change. No, I don't think circuit current will change. Because circuit current is in phase with resistance, or resistor. So by capacitance increasing, it will change the supply voltage. Oh, okay, it'll make the supply voltage less in phase with circuit current. So then the capacitor's capacity will increase, thus Z will increase at Z is equal to square root xc squared plus r squared. Thus Vs will be less in phase with I total. If Vs decreases and Z increases, then IT must decrease. However, I'm not confident in that answer. I might be big braining it, or I might be hella stupid. Inductors added. Oh, let's go. I love resonance. Inductors added a series of a capacitor and a resistor in the circuit. The reactance of the inductor is that, and the reactance of that capacitor is that. Thomas adjusts the frequency until current is maximum. Wait, is this the same question? Oh, no, never mind. Current is maximum, so that means we know Imax is equal to 0.399 or 339. So Imax is equal to 0.339 amps. Oh, we don't even need it. Because let's use this equation right here. I don't use this equation that often, but it's helpful. LC, so we got L and C. These are reactants. No! Wait. They don't give us much room, which is annoying. I don't know if he needs this at all. I want to find L is so. Oh, okay. Okay, so we know calculate resonant frequency. Resonant frequency will occur when XL equals to X. Thus, omega L will equal to 1 over omega C. So omega squared will equal to 1 over LC. I think I need to find... I'll find L and C. Actually, yeah, I don't really like this one. I'm not going to use this idea. I'm just going to find... Because what they've given us is... Here is XL and here is XC. So I'm just going to find L divided by 2 pi 1 equals L 23 times by 2 pi equals C. Okay. So here we go. 0.038 Henry. C is equal to oh my, hey, equal to a large number 22295.9 farads. And now we can use that other equation from before. 2 pi in the square root 0.038 multiplied by 22295.0.0376 square rooted divided by 2 pi divided by should answer. Oh my god, I think I might have done it wrong. So I got I did wrong. I know why. Oh yeah, it's actually pretty obvious. This is actually 1 over c. Yeah, so that's 1 over c. Oh no, I don't have the value anymore. Okay, so it's just let me see is equal to 1 over all of that function. That's how it works. 23.5 times 2 pi times 151. Let's look at a tiny number. Yes, the capacitance only equals 4.49 times 10 negative 5 farads. Right, so then we can plug it all into the equation again. 2 pi 4.49 times 5 multiplied by 0.038. We can find our resonant frequency. Okay, that's a good value. 1 to 1.91 hertz, which is equal to 1 to 2 hertz 3SF. Okay, my favorite question. Then what current is maximum at resonant frequency? Okay. At the resonant frequency, XL equal to XC. Thus, impedance is at a minimum as Z is equal to square root of R squared plus XL minus XC squared. Jam that in. Therefore, supply voltage is in phase with circuit current. Thus, all of the voltage would be vertical monitor. I'm just gonna change the monitor. Oh, no, we'll leave it. I'll zoom in though. Okay, go back to question 1. Okay, what did I say? The time constant is the time taken for the value of current or voltage to reach change by 63%. What did I say? T tau equals RC, so the time constant is the amount of time for the capacitor and circuit to change up to 63% of max charge. Oh my god. Okay, so I don't get the grade because I said the amount for the capacitor and the circuit to change. I don't know what that. Okay, so this should just be current Oh, you can't see that. Here I should really just be saying current or voltage. That's an. I would say I still said the right. I almost said the right thing. I just didn't say voltage or current. It's an N there. That's fine. We chillin'. We chillin'. Alright, we look here. Oh, look, I feel like it's just not. Full screen it on. Yeah, we'll just do that. Maybe I'll move myself this across. Yeah, that looks a lot nicer, I think. Okay. What did I say? That's the same answer. I got the energy correct. Only half the energy supplied by a cell is stored in the capacitor. The rest half is changed due to resistance. I didn't say due to resistance. However, I think I still get the tick. I gotta be honest here. But I would say due to resistance. I was thinking of saying resistance. If you run back tapes, I was thinking of it. But I didn't. Oh. Let's go. What did I say? What did I say? Okay, so if we move it back here. After one time constant 0.56, which is what we get here. You have to get both parts. So the second part, so this graph is correct. Graph of decay curve, exponential decay, same thing. Graph of decay curve, its capacitor begins to get charged. Its current is maximum. At the start of the reflow, later, more charge remains in the curve. Okay, so I said it wrong. But I had the right. I just didn't say enough. Yeah, this is one of my weaker points where don't just say enough of it. Yeah, that's a merit tick only for this part. This part I got incorrect. Pretty much what I should be saying is current is the max initially. When the rate of flow, the charge is the maximum. But yeah, as more okay, this is the part I always forget. As more charge that accumulates on the plates, the voltage in the capacitor increases, opposing the source voltage. This is back EMF essentially. Thus, it becomes way harder for the charge to accumulate on the plates to a point where you get zero charge. Boom, an R-tick right there. We got 1R, 2R, 3R, 3R. I think it's M6 right there. Let's check. M6 is 2A, 2M. However, I'm not sure if it's one of the papers where you can just say like 1A an achieved tick is. Yeah, this paper's a bit weird, but some papers you can be like achieved tick equals 1, merit tick equals 2, and excellence tick equals 3 points. For this paper, I'll just play it harsh and go 5 because technically it's 1A plus 2M. But like, I don't know. I'm just play harsh. Might as well. Voltage across the connector will be 0 as Christian. I'm a bum, bro. I don't know what I'm doing. The DC circuit will take a while for the current to reach maximum switch. Changing flux creates induced voltage that opposes the voltage moment. Press from increasing rapidly. Yeah. Said it correct. I would say increase. I would say rapidly might be a good word to use, but I kind of explained it in more in depth, so I think I get away with that. 0.2 henries. Boom, buddy. Boom. Got that shit right. That's a merit tick right there for that one. And then when the switch is open, current on the first call drops very quickly. Oh yeah, you were talking about transformers. Very rapid flux change to primary. Yeah, I never said it in like terms of primary and secondary. Oh, okay, okay, okay. Yeah, I get 2 achieve ticks, I think. Thus I get M6. A little bit gutted about that. But you know what? Wait, what? 5.2. Nah. No way, Jose. I did the RMS one wrong. Because it's AC. I'm okay. It's a learning progress, learning process of learning. You know what I mean? 122 hertz. I did get that right. I'm the goat. That's why. Capacitance will increase with dielectric constant, increase hence reactance. Oh, I never said XL. Oh no, I still get it though. I said I used a different example. Okay. And then we go to the next question. Resonance, reactance, inductor equal that. Yep, said that. Opposite phase. Cancelling each other out. I need to say that. Opposite phase cancelling each other out. I just never said that. Hence penis is equal to hence size. I don't know if I can even give myself a T-tick for that, but you know what? We'll give us a T-tick, but I just need to say cancelling out. I did never said it, but I did refer to it with impedance, because XL equals XC, and it's minusing. So cancelling out as their opposite phase. So what's that? 1T, 1 hour, 1A. That's 2E, 2 what? 2M, 1E. Bro, guys taking a laugh here. Okay, so I get. Oh my god, I get an M5 technically if I'm trying to be harsh on the smart grid. Okay. Let's say the predictions wasn't correct. 5, 6, 5. We get 16. In all honesty, even if I get a merit, I actually don't mind. Because doing 3 papers isn't gonna be easy. Yeah, I don't really know what to say. I don't even know what to say. Because like I'm really looking at it. Made a couple mistakes, like initially I never said current or voltage for the first part. The resistance, didn't say that correctly. There's a few things I just need to fix up, but for the most part I think my knowledge is correct. I look feel like this is a yap fest of the video. I don't even know if I'm gonna actually post this, but I might just post it just to see. Just to see if it's helpful to anyone. Okay, that's 2017 physics electricity paper. Done.